Good morning all. Today we are going to study the topic MMF of air gap and their numerical problems. We will start with the calculation of air gap MMF in the case of a smooth armature. As all of you are aware about the standard relation between B, H and nu, that is H is equal to B by nu, where H is actually the magnetizing force. We have already mentioned that in our previous slides. It is also said to be mmf per meter, which is indicated as small at. So the value of H for air gap can be found by using the standard relation, which is represented here. So this is H for the air gap, which is represented as small at suffix g, which is equal to average flux density in the air gap divided by the permeability. The permeability of air gap is nu 0 and its value is 4 pi into 10 raised to minus 7. After making this substitution and solving this, you will be able to get the mmf per meter for air gap is equal to 8 into 10 raised to 5 B average. That is actually the mmf per meter for air gap. The length of air gap is indicated as Lg. So the total mmf required for air gap length can be found out from this relation by multiplying it with Lg. Hence you will be obtaining the final relation as capital ATG. This is actually the mmf of air gap for the whole length Lg is equal to 8 into 10 raised to 5 B average Lg. This is the relation for mmf of air gap with smooth armature. Next we are going to study the mmf of air gap with slotted armature and radial ventilating ducts. From the previous video session, that is reluctance of air gap, you have studied that the reluctance of air gap with slotted armature and radial ventilating ducts is kg times that of reluctance of air gap with smooth armature. From the standard relation of mmf, that is mmf is equal to phi into reluctance, you can say the mmf of air gap with slotted armature and radial ventilating ducts is kg times that of mmf of air gap with smooth armature. Since the reluctance is kg times and mmf is equal to phi into reluctance. So you will be able to write the relation for mmf in this case as ATG is equal to 8 into 10 raised to 5 kg times B average into Lg. Instead of kg and Lg, you can write it as Lge, that is the effective gap length. So comparing with the standard relation for air gap mmf in the case of a smooth armature, in this case the air gap mmf is kg times, or else you can say that the air gap length has been increased by kg times, which is represented by effective air gap length, that is Lge. Since the air gap length has been increased by kg times, this term kg can also be said to be the gap expansion factor. In the same relation, instead of B average, that is the relation for flux density, if you are making the substitution as flux per unit area, so instead of B average, you are making the substitution flux per unit area and bringing the kg term to the denominator. This Ag by kg term together can be said to be Ag dash, which is actually the contracted air gap area. So if you are seeing with respect to the term Ag, the effect of kg on this relation can be said to be contraction in the air gap area by kg times. Hence this term kg can also be said to be the gap contraction factor. With respect to Lg, we say it as gap expansion factor, and with respect to Ag, we will say the term kg as gap contraction factor. In this standard relation, this phi is indicating the flux per pole and Ag is indicating the actual area of air gap per pole. Since Ag indicates the actual area of air gap per pole, the term Ag can be found out from this standard relation. In this relation, the slot pitch into gap core length alone indicates the area of air gap per slot. Since we have to find the area of air gap per pole, you have to multiply it with the number of slots per pole. Then you will be getting the term AG, that is the actual area of air gap per pole. In order to find the relation for AG dash, you have to divide it by kg, and the standard term for kg you have studied in the previous video session, that is OS by OS dash into L by L dash. Instead of slot pitch you can write it as OS, and instead of gap core length you can write it as capital L. You will be able to cancel this OS and this OS and this L and this L, and finally you will be getting the relation as slots per pole into OS dash into L dash. Definitely the term OS dash and the term L dash is less than that of OS and L. Hence the term AG dash will be definitely less than that of the magnitude of AG. From this it's clear that the effect of kg over here is the contraction in the air gap area by kg times. Hence kg can be also said to be the gap contraction factor with respect to the actual area of air gap. Next we are going to study the effect of saliency on the air gap MMF. This occurs in salient pole machines. You have studied about the construction of salient pole generator in your previous semesters, specifically in the topic synchronous machines. So if you analyze the construction of salient pole generator, you will be able to see very clearly there that the length of air gap is not uniform in the case of a salient pole generator. It is minimum at the pole center, and as we move away from the pole center towards the pole tip, the air gap length also keeps on increasing. Just like as shown in this figure, this portion can be considered as the pole center. Here the flux lines are almost uniform, and as we are moving towards the pole tip, the air gap length has been increased like this. See, the flux lines are starting from here, coming like this. So definitely this much will be the length of air gap. As the length of air gap is not uniform in the case of salient pole machine, definitely the flux distribution is also not uniform. From the standard relation of flux, you very well know that flux is equal to MMF by reluctance. As the length of air gap is minimum at the pole center, then definitely the reluctance at the pole center will be also minimum. Hence the maximum flux occurs at the pole center, and as we move towards the pole tip, since the air gap length has been increased, the reluctance will be also high, and definitely the flux distribution will be reduced. You will be able to see here there is more crowding of flux lines at the pole center, and as we are moving towards the pole tip, the crowding of flux lines has been reduced and the length of air gap is this much. That is, the length of air gap has been increased. So due to this saliency in the salient pole generator, you cannot say that the length of air gap is not uniform. The effective length of air gap can be said to be LGE is equal to kg saliency into actual length of air gap at the pole center. That is shown here. This is the flux distribution curve. It's very clear that the flux is maximum at the pole center, and as we are moving away from the pole center, the flux distribution is decreasing towards both the sides. So let's find out the air gap MMF in the case of a salient pole machine. Air gap MMF in the case of salient pole machine can be found out from the standard relation, that is MMF is equal to flux into reluctance. Let's find out the flux in the flux tube at the center. Flux tube is actually this flux lines. The relation for the flux in the flux tube at the center portion can be found out from the standard relation of flux density. That is, flux density is equal to flux per unit area. So from that, the flux can be found out. That is, flux is equal to flux density into area of flux tube. Flux density at the center portion is said to be Bg, as shown here. See, this is the center portion of the pole, and the flux density at the center portion is Bg. So you have found the flux in the flux tube at the center portion. Next you have to find the reluctance of flux tube at the center. Reluctance can be found out from the standard relation S is equal to L by nu 0 into A. So L here is effective length of air gap at center. which can be found out by using the term kg/lg, and instead of nu 0 you can make the substitution 4 pi into 10 raised to minus 7 and the area of flex tube at the center. So in order to find the MMF for air gap in salient pole machine, you have to multiply this flex term with this reluctance term. By multiplying these two terms, definitely the area of flex tubes gets cancelled, and finally you will be getting the relation as 8 into 10 raised to 5 kg bg lg. If the armature is slotted and provided with radial ventilating ducts, then definitely the kg term will be the multiplication of kgs, kgd and kg saliency. This kg saliency comes into picture only in the case of salient pole machines. As we have mentioned before, in the case of salient pole machine, the effective gap length can be said to be the product of kg saliency into lg. Hence, this term comes into picture only in the case of salient pole machine. You might feel that the MMF for air gap in salient pole machine, this relation is same as that of the MMF for air gap which we have studied before, but it's not that. In this relation, the term was B average, whereas in this case the term is not B average, it is BG. That is actually the flux density at the center portion of the pole. B average is actually the average value of magnetic flux density, which is shown by a dotted line here. From this it's very clear that this much is B average and this is BG, and the magnitude of BG is definitely greater than that of B average. So please don't get confused. In the case of salient pole machine, in the relation for air gap MMF, it's not B average, the term which you are using there, it is BG. Hence the relation is ATG is equal to, ATG is indicating the air gap MMF in salient pole machine is equal to 8 into 10 raised to 5 kg BG into lg. Next you have to see how to find out the value of BG. That is the flux density at the center of the pole. The term BG can be found out from the relation of form factor. The relation for form factor you have already studied. The form factor is defined as the ratio of average flux density to the maximum flux density. The maximum flux density is occurring at the center of the pole. So you can write the relation for Kf is equal to B average divided by Bg. This form factor is also indicated by psi, and it is equivalent to the ratio of pole arc to the pole pitch. From this relation you can write Bg is equal to B average by Kf, or Bg is equal to B average by psi. Average value of flux density over the pole pitch can be found out by using the relation flux per pole divided by pole pitch into length. That is actually the length of the core. This term has to be divided by psi. So instead you can multiply it with its reciprocal term that comes here, that is equal to pole pitch divided by pole arc. So in order to find the magnitude of Bg or the relation for Bg, for B average you will make this substitution, and for this psi you will be making the substitution pole pitch by pole arc. If you see here, this pole pitch and this pole pitch terms gets cancelled, and finally you will be left with flux per pole divided by pole arc into length of core. This is the relation which we will be using to find the magnitude of Bg. That is the maximum value of flux density which is occurring at the center of the pole. Once after finding the relation for Bg from this equation, we will be substituting it here and hence obtain the relation for air gap MMF in the case of a salient pole machine. Next we are going to see the net length of iron core. The armature cores are generally provided with a laminated structure. That is, it is made up of numerous sheet-like laminations which are being separated by a layer of mica insulation. So in order to calculate the net length of iron portion in the armature, you have to subtract the portion occupied by these insulations, Gross iron length when radial ventilating ducts are provided can be found out by using the relation L minus NdWd. But this will not be the net length of iron portion. In this term we haven't taken into consideration about the insulations which are being provided between the laminations. So the net iron length can be said to be Ki into L minus Nd into Wd, and this Ki term is said to be the stacking factor, and it is generally having a value of 0.9. It is defined as the ratio of actual length of iron in a laminated structure to the total axial length of the stack. Total axial length of the stack will be the length considering the insulation portion also. Actual length of iron in the stack will be the length without the insulation portion. So far in all the derivations, we haven't taken this stacking factor into consideration. That is, we have taken the total axial length of stack into consideration. But if in a problem stacking factor is given in specific, then definitely you have to use the net iron length, that is the term Li, instead of L. Next we are going to see the numerical problems. In this problem, the rotor is actually a slotted one, and the width of slot and width of tooth both are same, and length of air gap is also given. You are asked to find the effective length of air gap. Effective length of air gap can be found out from the relation kg into Lg. In our derivations we have used the notation Lge, but here it is written as Lgs. Both are one and the same. The value of Lg is given in the problem itself. You have to calculate the term kg. Nothing is mentioned about the radial ventilating ducts. As you know, kg is actually the product of kgs and kgd. Since there are no radial ventilating ducts, the term kgd can be said to be 1. So kg is effectively kgs. So you have to find the value of kgs first. That is the gap contraction factor for slots. Kgs can be found out from the standard relation, that is OS divided by OS minus KCS into WS. The relation to find KCS is given in the question itself, that is 1 by 1 plus 5 into Lg by Ws. That is the standard empirical formula which is used to calculate the value of KCS. Slot pitch is actually the center to center distance between the two slots. That can be found out by using the relation width of slot plus width of tooth. This was mentioned when we studied the reluctance of air gap in the case of open slots. So using this relation you will be able to find the slot pitch. Its value comes to be 0.028, and making the substitutions here you will be getting the term kgs, which is same as that of kg, and the value of Lg is given in the question itself. So by multiplying this kg with Lg you will be getting the effective air gap length. You have to solve it by yourself. In this problem, it is required to find the MMF. So while analyzing the question, you have to find it out whether it's a salient pole machine or not. In this question, it's very clearly given that the pole arc length is given. From this, it's very clear that it's a salient pole machine. Even though it's nowhere mentioned that it's a salient pole machine, if the pole arc is given in the question, you must consider it as a salient pole machine by default. So you have to use the standard relation 8 into 10 raised to 5 Bg Kg Lg, not B average. So first let's find Bg. Bg can be found out from the standard relation 5 divided by pole arc into length. This is the representation for pole arc, and you will be able to calculate the value of Bg here. Next you have to calculate the term Kg. For calculating the term kg, you have to see if it is both slotted and radial ventilating ducts are provided. Yes, radial ventilating ducts are there and it's slotted too. So definitely kg will be the product of kgs and kgd. So you have to find kgs and kgd separately. Kgs can be found out from the standard relation Ys by Ys minus Kcs Ws. Similarly, kgd can be found out from the standard relation L by L minus Kcd Nd Wd. Let's see if the magnitude of Kcs and Kcd is given in the question. See, it's given Carter's coefficient is 0.18 for opening per gap and is 0.28 for opening per gap. In this case, opening per gap is 1 and in this case, opening per gap is 2. Nowhere it's mentioned that this one is for slots and this one is for ducts. But Carter's coefficient's value is given for two different ratios, that is when the ratio's magnitude is 1 and when the ratio's magnitude is 2. In the case of slotting, this opening will be the slot width, whereas in the case of radial ventilating ducts, this opening will be the width of duct. So let's consider the case of slotting and substituting. Instead of opening, we will be substituting the width of slot and the air gap length we will be substituting here and we will be finding the ratio as 1. Similarly, in the case of ducts, for opening we will be substituting the value of width of duct and the gap length is same as that of here, that is air gap length. So if you are seeing in the case of duct, the ratio comes to be 2 and in the case of slot, this ratio comes to be 1. So this is actually the Carter's coefficient in the case of slotting and this is the Carter's coefficient we have to use in the case of radial ventilating ducts. By using that Carter's coefficient terms, we will be able to find the kgs and kgd. From there we can calculate kg. So after calculating bg, kg, and from the question the magnitude of Lg is given, by multiplying this with 8 into 10 raised to 5, we will be able to calculate the required MMF. This is another problem to calculate the MMF. Here the two conditions are there. One is the armature is smooth one. In the case of smooth armature, the magnitude of kg is 1 and you have to find the required MMF when the armature is slotted and the gap contraction factor is also given. In this problem also, if you analyze the question, you will be able to see this is actually the salient pole machine because the ratio of pole arc to pole pitch is given here. As I have mentioned in the previous problem, if something related to pole arc is given, then definitely you must consider such a problem as a salient pole machine. So here also, in order to find the required MMF, you have to use the relation BG instead of B average. You can calculate BG by using the standard relation, that is flux per pole arc into length. Since pole arc is not given here directly, you can find the pole arc magnitude from this relation, that is by multiplying 0.66 with pole pitch. You can calculate the magnitude of pole pitch by using the standard relation pi d divided by p. Pi d represents the overall perimeter of the machine, and if you are dividing with the total number of poles, definitely you will be able to find the pole pitch. The armature diameter is given in the question, so you have to make the substitution of d here as 0.25 and the total number of poles are also given. So from here you will be easily able to find the magnitude of pole pitch, and multiplying it with 0.66 you will be able to get pole arc. Making that substitution of pole arc here, you will be able to calculate BG and the value of kg is given in the question itself. With that, we are completing today's session. In the next class, we are going to study about MMF for teeth and real and apparent flux densities. Thank you.